Welcome everyone to today's webinar. We're just going to wait a few more moments here for everyone to join and we'll get started. Okay, I see some people trickling in here. Okay, I'm going to get going here. I'm sure people will join as we continue on. So, welcome everyone. I'm excited to go through this webinar with you all. I appreciate everybody taking the time to get out of their day in the middle of the week to come and join us with this talk. Please note that this event is being recorded. The link will be available via email after the webinar has concluded. So you won't be able to see or hear anybody else but me. But if you're not comfortable with the recording, we invite you to sign off. But today, we've had a great amount of people, sign up for this webinar. We have, I guess, last time I checked this morning, about an hour ago, we had 254 people sign up for the webinar, which is great. 38 countries, 194 companies, I think something like 45 industries. So, again, I appreciate everybody taking the time. I'm happy to have you all here. My name is Steven. I'm a product manager for Ganap Pro for Rust here at AdaCore. I'm a technical person, but I'm not an engineer. So please forgive me if there's anything that I say or can't answer, but I'm going to do my best throughout all of this. I started developing myself kind of in my spare time a couple of years ago. And specifically, I got into Rust by developing these micro SaaS applications for companies that I was working at as product manager. And I was curious what it had to offer. That's why I got into it. But I found it approachable, flexible, and as complicated as I wanted to make it. And so, I really am excited to kind of get into this with you all. So I'm going to move on to this next slide. I kind of want to go through, give a little some context about AdaCore, who AdaCore is. But before we get into this, I want to say if you have any questions during the presentation, please use the questions box at the bottom right of your interface. I'll add these questions, to kind of like the back end of this presentation and try to answer them with as much time as we have towards the end. If we can't get to those, anybody's questions, if we get, a bunch of them, then we'll, follow up with you via email with some answers. So AdaCore, for those of you who do not know AdaCore, we are a high integrity tool chain provider. We were founded in early 90s, 1994, and our roots go back to the 70s from a defense sponsored project to create Ada, a standardized memory safe language for mission critical applications. And since that time, we have expanded the scope of our offering to include, Spark, which is a subset of Ada, as you all know, C, C++, and now we're welcoming Rust into the family as of last year. So, very exciting. I'm a big enthusiast for Rust and open source in general. And I think that we're going to be able to bring a lot to, the table here with that. We work across many high integrity industries, including avionics, automotive, military defense, space rail, air traffic, and more. And frankly, we're continuing to expand and grow. It's exciting times for us as we turn this page into a new chapter. So, as I mentioned, we are a company of engineers and technical experts. Um, we focus on development, environment, verification tools, Ganap Pro, which is our suite of tools, mainly kind of the notable component of the Ganap Pro product is the compiler, Ganap SAS, which is our stack analysis tool, and Ganap DAS, which is our dynamic analysis tool. And of course, qualified tool chains, certified runtimes. We offer unparalleled support. And we don't have a support team. We have a team of engineers that provide support. So we're a team of experts globally, And overall, we offer this high integrity, safety critical embedded solutions for tool chains uh, across these different industries. So, moving forward, let's kind of talk about Gannett Pro for Rust, just kind of give you guys some context and some frame of reference for, before we jump into the project. Um, you know, Really just to kind of talk about Rust for those of you who are a little less aware of it, or maybe you don't know all of the dynamics of it. It was founded and, it was kind of created as a project by Braden Hoare back in 2006, 2009, kind of around that time. I think it's first from a frustration with a broken elevator and in his apartment. And he named Rust for, a fungi. Actually, they didn't know that fungi that are over engineered for survival, I think is what he said. Which is funny because it's so true. This is the way the language operates, but it's also, it brings a lot to the table and a really fresh take on uh, how you can program with it. And the first stable release was in May 2015. So we just had our 10-year anniversary since that stable release, and the Rust Foundation was founded in February 2021. So it offers a number of different things: type safety, memory safety. Think of for like type safety type items. In case you don't know the type safe, memory safe components, think of Rust from a type safe perspective as like a careful librarian. It makes you sign out exactly the right book before you read it in code terms. It kind of Rust forces you to be explicit about every data conversion or pointer usage. You can't accidentally treat a number like text or mix up two incompatible types, so you avoid those mysterious "it worked yesterday" bugs and that pop up in C, C++, things like that, when you pass the wrong thing to a function. So for memory safe, Rust is like having a built-in safety guardrail for your computer's memory. It tracks who owns each piece of data and when it's safe to drop or share it. So that kind of that leads to no more surprises like random crashes, data corruption, or hidden memory leaks because you forget to freeze something. You get rock solid stability, and you don't really incur any extra runtime slowdown because of it. There's multi-language interoperability. Again, we'll talk about that later with Gannett Pro's UPR build. But I think the most notable thing about Rust is its community. It's strong, it's buzzing, as you all probably have heard, and it has been ranked the most loved language in Stack Overflow for years now. The past 7 years, I think, going on 8. And of course, it's fun to work with. Again, as a product manager, I approached it just wanting to know more. Um, and I was able to get into it kind of in a simple way, but then I could dive down as deep as I wanted to later on, which is something I'm continuing to do and continuing to learn about for Rust. Something I should note too is that with that buzz, that momentum that's coming out, we have these different kind of initiatives that are being catching momentum from a governmental standpoint, in the Department of Defense and NSA, CSA, recently, they released information sheets, these cybersecurity information sheets. Since 2022, there's been this continual push every year. In 2024, last year, they started mentioning Rust by name. The White House released a mandate for safety critical. Um, Specifically naming Rust, and then again, just a month or so ago, um, the NSA and CISA released memory safe languages, reducing vulnerabilities in modern software development. Again, mentioning Rust, which is really cool. It's great that it's being mentioned by name, but of course, I understand that it's still kind of a young language when it comes to in a relative sense, and so it's important to note why they're mentioning it. It has a lot of benefits that aren't really present. Some are, some aren't, but it hones some rough edges that are out there, which is great. And so, again, this deck is going to be shared with everyone after the presentation. So there's going to be a lot of hyperlinks involved with this. People can go through it at their own speed. I encourage everyone to click through the links. We're also sharing these as we are talking. But if there's anything that anybody misses or wishes they clicked, you can get into the deck and click this later on. So yeah, I guess when it comes to Gannett Pro for Rust, just our product, it feels like upstream. It feels familiar. We're taking 30 years of experience supporting safety mission critical industries with ADA, Spark, CC++. We're bringing this to Rust, and we offer that support. Again, it's unparalleled. We actually have engineers that are supporting those that need the help, and we have yearly updates incorporating the most recent stable tested releases from upstream. Again, it's familiar. Everything you know now with formal industry support is there, including we bring SBOM and we bring that support to the table, so we can really start looking at this as the next chapter for Rust. So let me pull this up here, and without further ado, let's get into the actual rerouting program that we're going through, that the blog was about. Hopefully everybody was able to read through that. So the first part of this is, I came into Ada Core, and really learned a lot about, the, uh, I guess, the spirit of building things forward, seeing what languages are capable of, and looking at these projects that my colleagues have gone through. So these are all hyperlinks. Again, you'll get the deck so you can click through these. But I was able to learn about the history of these previous Rover projects, which I love to see. I mean, it's really inspiring. And so, being someone who is supporting Rust as a language, is pushing it forward and evangelizing for it, because I really am passionate about it. I really wanted to just try something new. I wanted to push this onto a new project with the Rover and develop this rerouting system. We have a long history in this, which is great. But frankly, we just want to take this Rover project further by developing a path finding algorithm that would chart an optimal path from a start node to an end goal node given initial data, and adjust the charted path on the fly. So as new information became available, aka obstacles, the pathfinding algorithm would replan and account for that, and negotiate around those things in an optimal way. So again, we'll share these slides. So if anybody wants to click into those, I would encourage it, and read a little bit more about some of the other work we've done with the Rover and other demos. So breaking the project into pieces, I thought it was important to make sure I did this in kind of chapters for myself, so I can understand, how we were going to do this. Obviously, choosing Rust was important. I'm a little biased here, but of course, I wanted to understand what it was capable of. I knew there's a lot more for me to learn as an individual, but I also wanted to see if it was, if I could challenge it in a way, and put it to the test. I wanted to make sure I could see what it was capable of. The next step was, choosing the algorithm. Um, Picking a pathfinding algorithm out of a sea of options was not easy, but of course, once I started reading more about it, it became a little bit more clear. The balance there was finding something that was familiar, and not too exotic, but also meets the needs of our project from a computational and complexity middle ground that I was looking for. Third was adapting the code. So obviously taking the algorithm, breaking it out, understanding it, and then rewriting it in Rust and seeing how that could actually be done. And again, the last part of this is, of course, thinking forward and to what we want to do in the future. What's possible? What are the things that we kind of have in our mind? Specifically, putting this on a rover, like an actual robot, and seeing it drive around and reroute, and then maybe even scale out into bigger, more complex algorithms, introducing a whole lot of other complexities that may be there. So leaving a little bit of room there for some wiggle room for some scale up considerations. So when it comes to the algorithms, there's a lot here that, again, there's a sea of options out there, but I kind of wanted to go back to where it all kind of started. Dijkstra, if you all are familiar with pathfinding algorithms, Dijkstra's algorithm was found, I guess he started that in the like the early, I think the mid 50s, if I'm not mistaken. And then later on in the 60s, that was taken and used to develop a star. Now, Dijkstra's algorithm is kind of like, it follows the it's a greedy algorithm. It's problem solving heuristic that makes locally optimal choices at each point. So it sounds familiar to those working in data and AI, generative models, things like gradient descent. It's seen in computer science programs. Sometimes I hear about people taking this and trying to make their own in a way to to kind of understand that. You'll see it in gaming, and again, it feels like data and AI. This is kind of following you know the the traveling salesman, I guess, model, where at each new step you go to the closest city that has not been visited. And so that's kind of what A-star does. It is an improvement on Dijkstra's algorithm. However, it is a static graph search and it cannot recompute given new data. So that wasn't necessarily going to meet our needs, but if I were to skip forward to and look at what NASA did for the actual Mars Discovery rover, and even Ingenuity, you'll see that they're using field D star, which is a dynamic A star or D star developed in '94, and then that moved kind of evolved into focus D star in '95 and 2001 life long planning LPA star or LPA, which is what D Star Lite uses. Um, I love Field D Star. I think it's incredibly interesting. However, given the parameters and what we're needing as dependencies and requirements for our project, it was computationally hungry. It's going to be kind of sapping our resources, but then it's also going to be uh, a little bit overkill. I think it's just a little bit more than what we need. So the middle ground is that D-star light. Field D-star uses potential field gradient method and does these smooth continuous trajectories. Doesn't necessarily kind of clicks out of the grid-based structure, but D-star light still uses these incremental search heuristics. So we can account for new data and replan, and then we can design for dynamic maps. So always kind of updating. So, and you can kind of see through some of these other items that I feel like it was a good middle ground, kind of a Goldilocks zone, if you will, for our algorithm. So we chose D-Star Light. So I'm going to share something real quick. I created a web interface. Let me go ahead and share my screen real quick with this here. All right. So as you can see, this is a simulator that I created. It is, it's completely written in Rust using WebAssembly and U and a couple of other crates and bindings. Use a framework that's similar to React. So people who are familiar with React can see this and understand a little bit better. It feels familiar to them. And obviously over here on the left side, we can choose which algorithm we want to use, and that will help us visualize what's going on here. We can choose light and dark mode if we wanted to. I thought that was a little fun addition. Um, and from here we can build the map, right? And we can see what's going on. I kind of have this map pre-built. You can constraints of time, but you can see there's a goal node, there's a start node over here that the this amber brown circle, which represents the rover, is sitting on, and that orange circle that is surrounding it is representative of the sensor that might be on the rover. So it's what it can see, quote unquote. So we kind of created this. We can create a little bit more of a few more barriers, kind of make it a little bit more tricky for it to find its way there. And from there, we can ask it to find a path. And so you'll see that it will use this and will find a path, and most ideal path to the goal node. And from there, we'll ask it to start its journey. So you'll see it moving along this path here, and we can add little obstacles here across the way. And as things continue to, as it moves along its path, you can see that as it comes into the circumference of its sensor, it will have to plan around those obstacles. The ones over here are not getting into that, and so they're not converting into something that it will need to plan around. And it will add these, data points to a node list, and it's always referencing this updated node list, where these dynamic obstacles are converted into these static obstacle blocks. This is using a 4-layer architecture. what I call a memoryless state for the layer that the rover actually sits on. And essentially, I say memoryless because it has no idea where it's been. There's another layer that keeps track of all this information. And, from there, we want to say, it will always reference that, but it's always replanning. So at each new cell that it moves to, it will think that it's its first, the start node. So it's always thinking that it's restarting on each new step and using the algorithm that we've chosen to then find its way to the goal node. You can see how it's, we've did a little rerouting through this and it had to optimally change its path. So that's kind of the little demo I made right here, just so we can understand and visualize here what is going to happen once we can, put the algorithm in motion. And it helps us be able to see forward too, when we want to actually put this on a rover and see how it will react, and allow us to understand the logic behind these things. Again, I'm not going to go into the big four-layer architecture components of this, but let me disable my screen sharing so we can go back to this. So here, let me pull this up here. So yes, so let me move to the next slide. Again, this is a simulation built completely in Rust using Blossom and U. Again, it's similar. U is similar to React or Elm. If you're familiar with that, it's low-level bytecode. It compiles the Rust code into WebAssembly. And so again, we can choose between those algorithms, implement that four-layer architecture, and get us to where we need to go with this memoryless routing state. So we'll share this deck. I encourage everyone to go and check that GitHub link out. That's where the rest of the project lives, including that documentation for the four-layer architecture, if you're curious about that, including the algorithm that we'll get into in just a moment. So again, getting into the algorithm itself. Just to simplify it, in the spirit of presenting the information, not overwhelming the conversation, I've broken the implementation into 9 distinct sections, but even further down into chunks, kind of these intuitive chunks where we outline types, init, loop, reconstruct, and glue, and how these different components talk to each other. So as I've mentioned, the startup new builds the map using the data we fed to it. It pushes the goal node to the open list. Then the replanning loop, it drives the open list until start is consistent. So the calculate key, compute the one-step look ahead, which is the RHS, and the update vertex list, and then we'll get to the path extraction, where once its open list is converged, we'll reconstruct the path, it will pull and apply those optimal routes based off of the new data that it has. So that's the rover getting to a new cell, understanding its surroundings, and converting anything that is a new data point that doesn't have the data from the original static map that we put in place before we said find a path. And then we have these dynamic updates. So whenever a new obstacle is seen, again, update obstacle is called, tweaks the grid, and the one-step look ahead, the RHS of affected cells, and then lazy insert then updates the cells into the open list of nodes, and the subsequent compute path resumes from previous state. So again, reusing, it's that lazy look at it, reusing nearly all past work. So one of the interesting things about this too is the ownership and borrow rules. No two functions can simultaneously corrupt the same maps or heaps. And since every unwrapped peak is guarded, we'll never panic at runtime in a predictable release mode build. And we see this lazy removal when we update vertex is implemented. Okay, great. So here you see our lazy removal. Hopefully everybody can see this okay. It's not too dark. Here our lazy removal step in update vertex. You can see rather than delete from the heap, which is expensive, we simply push a new version of the state. I kind of have this that line highlighted, that self open list push state. So yeah, it's expensive. We simply push a new version of this state. So self open list, that little line highlighted there is where D-Starlight reuses past work. Now with Rust hooks, notice every method that changes our maps or heaps takes this borrow self mutably or that the signature token that ampersand mute self, where the compiler guarantees exclusive mutable access. Rust compiler forces me to declare I'm about to mutate state, so there's no accidental shared mutate. There's one of our core safety hooks, and it's an important thing to call out because this is something that Rust really helps with. And something that I find very interesting with Rust is the traits component. Now, uh, we have these different, I have a few slides on this. So, traits, on this compute path um, generates a route given the initial data. And it spits out none if compute path cannot find a path to reach the goal. So if we were to go back to that virtual simulation, if it can't find an optimal path to the goal, if it's blocked in every way, then it will throw an error and say you can't reach the goal, find another map or redraw it. And then update obstacle notifies the planner of changes. And so notice we use an associated type chord to each implementation, so it can pick its own coordination type. So in like type safety, the compiler enforces that and you can't mix coordinate types by accident, essentially. So the actual implementing of this, dstar light struct implements the trait, right? So satisfying the contract, we get zero cost abstractions, no virtual calls, no runtime dispatch and release builds, just static inlighting providing static guarantees. If you forget a method, it won't compile. Now, the actual compiling of it, once during the compilation, we can have a generic navigate function over NEP Pathfinder. We won't have to touch our orchestration code at all, since Rust monomorphizes this, allowing our pathfinding method to be interchangeable, allows us to scale to a new pathfinding methods. Field D star or any flavor of pathfinding algorithm, we can modularly put in place for this. So this is again the scaling component of it. If we wanted to go field D star or want have some kind of vector generation or trajectory generation component that we implement later, we can do that. The trait pattern, intrinsic to Rust, it highlights several strengths. We have these static guarantees, where if you forget a method, it won't compile, as we just outlined, these zero cost traits with no dynamic overhead and the type safety. So the compiler enforces that you can't mix coordinate types by accident. So again, there's a lot more to the algorithm. I kind of cherry picked a few of these sections, but I obviously want to encourage everybody to get into the blog as well. I call out some other areas as well, like uh, various different components, as I mentioned in the beginning, in these 9 different sections. So let me pull this up and just change it. Right. So again, Rust borrow checker. Notice that the this ampersand mute self here, which is the borrow self mutably signature token, it forces me to declare every mutation. The ampersand itself on the signature, it can't accidentally alias or concurrently mutate state. So the outcome, I can't accidentally share or alias these maps or heaps, which is a great thing to be able to say that I don't have to worry about, because obviously that can cause many different issues. In memory efficiency, we only share reachable neighbors once up front. We don't rescan the grid on every cost or successor call. Again, memory list state. The rover sitting this one layer, but then we also have this the state where it's a little bit, that lazy removal where it has this ongoing updating prioritized list of blocks. So the outcome, minimal memory that is being used and no redundant allocations. And then incremental update management. Obviously this one line in our lazy removal trick, it only reinserts the few changed nodes instead of throwing away the whole heap. So it's huge CPU savings on replanning. So another thing I noticed is obviously the traits and zero cost abstractions. Um, by defining a pathfinder trait and implementing it for D star light and a star or field D star, anyone you want to use, Rust generates direct calls. So this pathfinder trait is our compile time contract, no V tables, no runtime penalties, so that zero cost abstraction is guaranteed. So, we've sidestepped those things, the vtables runtime penalties, which is a good added bonus. Then we have the abstraction and flexibility. Because navigate is generic, I can swap algorithms at compile time, and some orchestration code drives, any planner that we have in place. And again, that kind of allows us to have zero overhead. Oops, sorry, this one. So from the algorithmic optimization standpoint, scaling floats to integers gives us a total and consistent ordering in our heap. So we multiply floats, as you can see here, we multiply floats by 1,000 and cast to 64-bit integers, and that gives us a total consistent ordering for our heaps. Keys avoiding, NAND and rounding pitfalls. So, outcome there is we're avoiding those traps and rounding out the bugs, which is, obviously something that is going to benefit us in many different ways. And kind of like the last slide from our carve outs here is type safety. So intrinsic with Rust, type safety, we have we can see here that there's a named coordinate type, and by aliasing usize, and as chord, the compiler won't let me mix up X and Y or slip in negative indices. Everything is checked at compile time, as opposed to in runtime, which is critical and a huge cost saver ultimately. And we have this error reduction component to it as well, where we never drop into an unsafe block. Nowhere in our D star light implementation do we ever write unsafe. And that means we've built a fully functional incremental path finder without ever dropping down to raw pointers or manual bounds checks. Um, so again, you can, when you get into the GitHub repository, look at the algorithm itself, and if you want to scan through that, you'll never see an unsafe block. So that's 100% safe for us, which is huge for certifiable safety critical applications. And the third here is predictable performance. Heap pushes and pops are always O log n, which means no hidden quadratic scans, heap pushes and pops. And so our worst case runtime is clear, bounded, and testable, which allows us to move fast and be confident in what we're doing here. So future plans, following the plan when we were outlining the project, again, being able to scale up, I'd like to be eventually able to push this Rust path finding system into a Rover robot. I'm actually building one now. I have, my office is strewn with hardware components, and I'm going to be putting this together. And once that Rover is built, I'll be looking to add different components to this too, like a machine learning element by incorporating an AI camera and the Rust TF Lite, binding, so the rover can actually use computer vision to detect, identify, and plan around obstacles in the real world. And we're going to have different mixtures of that. There's going to be different iterations of this project, and this is just the beginning. And so later we'll be dropping the rover in the field to run tests. And again, I'll talk about this a little bit more later, but we'll be in September, we'll be at Denver Tech Day, and I'll be there in person, be able to show the rover in person and how it actually works, which I encourage everyone to look at that. And we'll provide a link later on in the conversation. Um, and future iterations, I can also see the algorithm scale up to more sophisticated methods, as I mentioned, field T star, trajectory generation, or some other different techniques that we might deem interesting to go play around with. And as we evolve the program to aerial or submersible vehicles, it would be curious, it'd be very interesting to see how how it performs. So again, as we move things forward with Rust, with these projects, they're fun, but it's also there's something that we're trying to accomplish too. We're understanding where the pitfalls are. We're understanding the nature of Rust and how it applies to safety critical applications, how it can help in industry, in real life applications that are mission critical. And so as we progress as a company, um, Gannett Pro for Rust, we have many different things that we're working on now that are exciting. As we scale out the project and its future iterations, we'll be supporting Rust growth in safety critical software. We're going to continue to push the boundary forward of Rust maturity in the mission critical space. And so, we'll obviously have this multi-language support. We have the ability to interface Rust code with Ada, C, C++ with GPR build. Version support from 1.85 or greater, including a full edition 2024 support, merging and bringing in new platforms such as Linux and Windows hosted VxWorks 7 and 64-bit QNX 8. Excited, really, I'm excited. I think we're all here excited at Adacore about GNAT coverage updates and where we are bringing MCDC coverage to for Rust and GNAT DAS Suite 26. That's going to help us in big ways as we move the ball forward internally and externally. And these updates are huge wins as it gets us to the point where Rust is certifiable, and particularly the MCDC coverage, which is, I'm personally excited about. Yeah, so again, to kind of cover really quickly, where our certifiable support lands. We offer certification needs across aviation, rail, space, industrial, automotive, and more. We have qualified tools, yes. Runtime libraries, yes. Certification materials, yes. Gannett Pro offers these assurance and sustained branched solutions, and I'm just checking a lot of boxes right now, and especially this is in mind from the certifiable component. So what does it get or take to get Rust to a certifiable state? Can move that to this. We have three major components. Obviously, the language and toolchain stability, toolchain integrity, target and platform support from engineering considerations. And support considerations, again, checking boxes here at Adacore with this. I'm seeing a lot of talk about where the support is kind of lacking sometimes. The community is vibrant, they do a great job. And we want to take things further by providing long-term support and professional support for the tool chain and supporting tools, but not just from the support team, but from engineers who are specialists in these things. And obviously, the qualification of the tool chain, certification of language runtime, and qualified support tools. These are all things that are happening now. We're moving things forward, and it sounds like Adacore is checking a lot of boxes, like I mentioned, and we'll continue to do so as we bring Gannett Pro for Rust to parity with our offerings in Ada, Spark, and C, C++. Again, what's included just gives you a look really quick, and it gives you all the pieces you expect, including shipping all the tools and libraries you need. The compiler Rust-C, we shipped, I want to call this out too, 1772 and Gannett Pro for Rust 25. In December, a CVE was open against Rust-C, and that impacted, 1772. And rather than our users move to a newer version of Rust-C to get the fix, we backported it. And so customers can stay on their selected tool chain and still benefit from the security fix. And then, obviously, we want to lean further into how we offer this, SBOM, this professional support. And if you want multi-language support, we'll help you do that with GPR build. Um, to take it a step further, we are avid participants in the Rust Foundation Safety Critical Consortium, the SEC, meeting weekly in most cases, which is it's an open working group. And obviously our aim is to progress Rust and safety critical software. We have subcommittees in tooling, coding guidelines, liaison. And again, we meet most weeks. I encourage everyone here who's interested to visit this GitHub page, the Zulip instance, and get involved if you're curious or interested, and haven't done so already. And so, just to kind of get to a wrapping up point here. these are the things that we guarantee we want to make sure that we are pushing and highlighting for everyone here about what Gannett Pro for Rust brings to the table, what AdaCore brings to the table from a stability, software supply chain security, expert support, long-term support, platform support, and existing code bases. Again, going back to the certifiable checkboxes that AdaCore goes through. Um, so that's it, everyone. That concludes our main presentation. And if you'd like to follow the rest of our mission with the Rust M.A.R.S rover, you can sign up to join the next webinar now, and look for updates in blogs by following AdaCore or LinkedIn, or checking blog.adacore.com. And obviously, if anybody has any questions beyond this, please, I encourage everyone to visit info or adacore.com, or send a message to info@adacore.com, and we're happy to answer those questions. But I want to also call out that if you are interested in following along with this project and seeing where we take things, again, I mentioned we're going to be pulling this algorithm into the rover. We have this project that we're going to continue to scale out and do different things with that are fun and exciting, but also showcase what Rust is capable of. I am going to be in Denver in September, along with the rover, and show the progress in person, and where we're at. Make sure not to miss that. It's going to be exciting. It's going to be fun, and we'll be demonstrating how it will reroute and do all sorts of other fun things while we're there. There'll also be some great critical software talks and demos on everything from static and dynamic analysis to cybersecurity and certification. So check out that agenda on our website, and please join that. Click that link and join if you're interested in attending. And so now we'll move on to our final Q&A section. I have gone a little bit over, but I of course want to see if I can answer a few questions. And again, if I can't get to all the questions here, then we will answer those up in just a little bit. Okay. So let me pull that up here so I can see these questions. I'm going to start at the top here. So Alexander, is there any use cases for cannot prove for Rust, or borrow checker is enough? I think that when it comes to that, I really believe that we have a lot of different safety checks in place with Rust just out of the box. We have, if we're looking at gonna approve for Rust, the bar check is great. It offers, a lot of safety and a lot of, performance improvements. But frankly, get out prove and other subsequent methods allows us to be a little bit more sophisticated and nuanced with where we're going with this. And it's allowing us to progress the static analysis component in Rust a little bit further. We won't be able to compile before we ship things. There's a Rust analyzer that you can get in VS Code. But Proof takes it a little bit further with those as well. Mikhail, this is about M.A.R.S rover root algorithm, but we see demonstration in WebAssembly. The Rust Gannett is supposed to be for microcontrollers. Why don't we see demonstration on an MCU? I'd like to see performance and code sizes. Sure. That's something that we can, if I had more time, I would have gone into things a little bit more. I think probably in future iterations, I think this summer I'm going to be releasing a video where I'll be able to, kind of be a little bit more tighter with my time and what all the material, and maybe even go through some of these things. So I'm happy to go through that. And so that's a good suggestion. I like that. Let's see here. And that might even be something that we can bring forward into that tech day. We'll talk more about that. And I believe that's pronounced read, Ryad. Apologies if I'm getting that incorrect. In the first run, does the rover have an initial graph of the landscape it will traverse? Shouldn't it build the graph as it goes? Yes. So we do feed it data. So we feed it data initially. So if you look at that back at that, the the obstacles that we drew on the map, that is then sent to the rover as initial information. Of course, you could just send it on its way and it can replan as it goes. If it just thinks that there's a straight path to the node, the end goal node, then that will that it will get there as fast as possible. But if it encounters things, it can still replan accordingly. So it doesn't have to necessarily have that initial data. It can work without it. But again, this is also kind of a demonstratable way of showing that you can add static information to the list and it can be updated in real time in that lazy removal way. And Andrea, what architectures will be available at ECSS space standard certification? Great question. I don't have the answer for that. I think we are discussing it as a team right now. So we can get back to that question later via email, Andrea. Happy to answer that later. David, I think we answered Graham's. Yeah, and how does Adacore compiler solution contrast with the open source one? I outlined that a couple of times in the presentation. I think that there's some, specific nuances there and some major differences too. But importantly, it doesn't feel unfamiliar. We bring it to parity with what we offer from a support and long-term support component, and making the tool chain certifiable, and helping it be that way. But of course, we want to make sure that it feels familiar to open source, to the upstream versions that everybody is used to. So in essence, there is no real contrast. You can get in there, initiate it the same way you usually do. It is not an unfamiliar statement. If there's anything that you do have question wise, we'll have awesome documentation and support to help you along the way. Okay. And then Matthew, which target PICs and MCs does the compiler support? I don't know off the top of my head. I'm happy to answer that via email a little bit later on, Matthew. I apologize. Is there anything I missed up here? David said part 2 registration form is broken, can't submit the form. Okay, we'll follow up with everybody if they can't get in. I think we'll probably send a follow-up via email for the registration for part 2. Okay. Well, I think that's all the questions, if I'm not mistaken. I appreciate everybody coming today. This has been awesome. I appreciate all the attendance. We still have 74, 75 people here, so hopefully I didn't bore everybody. I appreciate everybody's time today. I'm looking forward to the future versions of this, and hopefully meeting some of you along the way, and maybe we'll see you out at Denver Tech Day soon. And again, I want to thank everybody for coming and spending time with me. Hope you all have a great day. Thanks so much.